Start. Okay. So, good afternoon, all of you. We are going to start with this last chapter, energy methods. Now, this chapter is completely different from the previous chapters. So, not just in the sense that the way that we are going to discuss it within the scope of this second year mechanics of solids, but in general, there are two broad ways in which mechanics can be done. One is the Newtonian mechanics kind of way, which you are all familiar with, and the other is this energy methods kind of way, which is due to Lagrange and the other French people. So you have had some introduction to it in your +2 physics when you did the conservation of energy thing, because you must have realized then that the conservation of energy almost seems like a hack, uh, like a cheat code into doing things in a very easy fashion. But you have to be careful in how you implement it. So, in that spirit, we are going to continue with energy methods, but as you will see that we are going to go beyond that conservation of energy thing which you learned in your +2 physics. But before we can get into that, we have to wade our way through some preliminaries, through some fundamental things. Now, as I have told you earlier, that overall in mechanics you have these two broad approaches. One is this Newtonian mechanics kind of thing, and the other is this Lagrangian mechanics kind of thing. Now, in this Lagrangian mechanics, many things become very simple, but the price that you pay for doing the implementation simply is that the fundamental theory is very rich and sophisticated. So you have to wrap your head around it a little bit. Another thing is that in this Lagrangian mechanics, in this energy methods kind of approach, it really is energy methods. So in which subject do you study energy things most? Things related to energy, heat, work, all these things more. In thermodynamics, in which you have your class test today. Okay, so it is like God's will that we are starting it today on this auspicious occasion of thermodynamics class test, that we will start this chapter with a quick recap of the first law of thermodynamics only. And again, this has to do with how this entire branch of mechanics is dealt with. Later on, if you do higher studies and you study something like continuum mechanics, you will actually get to study from books which are titled like this, continuum mechanics and thermodynamics. Okay, so now it seems like thermodynamics is completely different, solid mechanics is completely different. Okay, but it is not like that. Okay, so everything is unified. It is only because of logistical reasons that when we first teach you these things, they are kept separate. But as you grow older, you will see that everything just mixes up all together. Okay, so energy methods. We'll start with the first law of thermodynamics, and you will see how beautifully it blends into things which you already know, which you don't know, and something which you will study. So just to give you a brief glimpse into the future, we'll study something called the Castigliono's theorem. So Castigliano was an Italian mathematician, engineer, and this makes certain problems very, very easy to solve. Okay, very, very easy to solve. You won't believe it, how easy it becomes. So it will be a very good friend of ours. But first, the preliminaries. So first law of thermodynamics. Now we are not going to study first law of thermodynamics in a very pedantic way as it is done in a thermodynamics course. You tell me very simply what it is. What it is, some kind of a balance, right? What does it balance? Okay, energy balance. So if I have to write it down, then what should be the ingredients in that balance? One work should be there. Okay, one work ingredient should be there, one heat ingredient should be there, and then they should contribute to some energy. Okay, okay. Now please remove this from this video, okay, what I'm going to say. So whatever I teach you, you keep this in mechanics of solids only. The way that your thermodynamics teachers have taught you, you learn that, and you please do your test in that way. Just because today only I'm teaching these things, please do not muddle up these two things. Okay, so please follow whatever your teacher has done. So work done, okay, plus Q, okay. This is going to be equal to what? It should be some change in energy. Okay, it should be some change in energy, but we will just decompose it into two parts. One is, this is what? Change in internal energy. Very good. Change in internal energy plus, what is this? Change in kinetic energy. Okay. We want to deal with this explicitly because after all we are doing solid mechanics, and in solid mechanics actual bodies should be there, not just the piston and cylinder. So we want this. Okay. Now immediately after this we are going to specialize to what we need in mechanics of solids, the way that we have been dealing with it. Okay. So the first thing that we are going to say is that you forget tutorial sheet 0. Okay, why? Because we are going to consider adiabatic things. Okay, so no Q. Okay, so no heat input into the system, no heat taken out from the system. Next, we are going to say that things are in static equilibrium. This is again an assumption that we have been working with all throughout this course. Things are in static equilibrium. We are not doing any dynamics. Again, I want to reiterate that just because we are doing within the scope of this second year solid mechanics things which are in static equilibrium, it does not mean that solid mechanics can only be done with things which are static. You can very much have solid mechanics which involve things in motion. Okay. So what we end up with is W is equal to delta U. So the work that we input, okay, the work done on the system, that will result in a change in the internal energy. That's it. That's what we are going to work with. Now, this is the part where we need to be a little bit careful. You all know how work is done, but when I discuss that, you will see that many things are very familiar. But this delta U thing, we have to be a little bit careful. So the kinds of systems that we are going to be dealing with in the context of mechanics of solids will be elastic systems. It is not necessary that it has to be elastic system only, but we are choosing to work with elastic systems for now. Now, what is an elastic system? Or what is an elastic material?
Please define what is that W? It is by the system
on the system. Work done on the system. Okay, so you tell me this thing. What is an elastic system or what is an elastic material? Material which follows? Absolutely no. So a material which follows Hooke's law is very much an elastic material. But if I ask what is an elastic material, please don't say that something which follows Hooke's law. Okay, so that is not the definition. Okay, so I will give you one general definition. Please keep it in mind, but please also be flexible, especially when you have to face CDC. Okay, one day you'll have to face CDC. So the people who will be asking you such a question may expect a different kind of answer. Don't give funda to them. Get the job, then you give funda to the whole world. Okay, so this is for a very theoretical, very academic kind of definition I'm going to give you. So basically, an elastic system is one or an elastic material is one in which the internal forces are conservative. There is a further addition to it. It is conservative in the kinetic sense, but we will not go into that. Okay. So an elastic material is one which is in which the internal forces are conservative. You know conservative forces from your plus 2 physics. So it is in that sense exactly what I'm talking about. Okay. So you can please write it down. So an elastic material is one in which the internal forces are conservative. Now there is a two-step logic to it. Okay, listen to it very carefully. If internal forces, or if you encounter forces which are conservative in nature, okay, I repeat, if you encounter forces which are conservative in nature, can you not associate some kind of a potential associated with it? If forces are conservative, you can associate a potential with it. Okay, all right. If a force if a force is conservative, a potential can be associated with it. Now, we had just now said that an elastic material is one in which the internal forces are conservative. So, in an elastic material, in which the internal forces are conservative in nature, we can similarly associate potentials. So logic is very simple. If a force is conservative, then we can associate a potential with it. We are already defining an elastic material as one in which the internal forces are conservative. So if those internal forces in an elastic material are conservative, then we can associate potentials with them. Okay, as simple as that. Nothing special. Okay. Now, these potentials that we just mentioned, we are saying potential, we can say potential energy also. Okay. So this potential energy which is associated with the internal forces, that is what is referred to as the strain energy of the elastic system. Okay. So This is what is referred to as the strain energy. Now, you may be thinking that I had started with the first law of thermodynamics. I had talked about the relationship between the work done and the internal energy. Then suddenly, why am I talking about this strain energy? Well, only one small logical step is left, where we say that for these kinds of elastic materials, the internal energy and the strain energy, they differ only by an additive constant. Okay. They differ only by an additive constant. So if we say that the strain energy is, let's say, U bar, and the internal energy is U, okay, so if we say this is U bar, then U bar is something just like U plus C. Please do not ask me to discuss what this is and how we can get into it. We'll not discuss it. Okay, it is a choice. Please accept it on good faith. So U bar is equal to U plus C. If that is so, then is it not true that this must be true? Okay, this must be true. Now, if this is true, what we are going to say, so all this mumbo jumbo thing that I'm saying, it is only to arrive at this fact that when we are dealing with the work done on an elastic material, although from the first law of thermodynamics, it tells us that it is the change in the internal energy, but operationally, we will understand that that work done is basically nothing but the change in the strain energy. So from now on, the capital U will depict the change in the strain energy. That's it. Okay. So therefore, from now on, we'll understand that this delta U is the change in the strain energy. Okay. From now on, the actual mechanics starts. So when I teach advanced mechanics of solids, we go into all sorts of proofs and mathematical things. We'll not do those things here. Okay. So at the second year, we will take a very utilitarian kind of approach. We will learn in the way that it will be most useful for us to solve problems. Okay. So as quickly as possible, we want to reach that stage. So towards that end, what we'll do is we'll take things in a very, very simple fashion. We want to find out how we can exploit that delta, sorry, that is, there is nothing called delta W, okay? Please make this correction. Work is work done, yes.
SQ was equal to change in energy.
Sorry?
From first one, SQ equal to change in energy. Then we have this strain energy and some internal energy. So,
No, strain energy is subsumed within internal energy.
so The other things are
Oh, it's only an additive constant. Okay, it doesn't really change in that delta. Okay, if you take the absolute values of the internal energy, if you can just calculate it, like sit down and calculate like God given power, then internal energy and strain energy will come out with a little bit of a difference. Okay, but as you do the work on it, that difference is not going to change. Okay, so what we'll do is we'll try to understand that W is equal to delta U in a very neat and clean fashion. For that, what we'll do is we'll take a rod, as simple as that. We'll take a rod and we'll try to find out what is the change in the internal or the change in the strain energy of this rod as we pull on it. Why pull on it? Because if we pull on it, then our mechanical system being this, when we pull on it, we are doing work on this system. Okay, we are doing work on this system. So that work done on the system is stored as the strain energy of the system. Okay, so we want to have this relation explicitly clear before us. Now, this is a very, very important point. When we write like this, that this is the force P balanced by another force P in the opposite direction, we will not think of it that suddenly that entire force P is applied on the rod. Rather, some amount of force is applied and that is gradually increased to the force P. Okay, everything happening quasi-statically. Okay, now another very important thing that we are going to tell ourselves is that the behavior is going to be linear. Behavior is going to be linear means the relationship between the deformation of this rod and the force, it is going to be a linear behavior. Okay, so what do I mean by that? Let us say that when the entire force P has been applied, then the total deformation or the total lengthening of the rod is delta. Okay, so when delta, so for the total deformation delta, the force is P. Okay, absolutely like unitary method which you learned in your high school. But if the deformation is some x, then the force is going to be P divided by delta into x. This is going to be the force. It is because of this kind of relationship that we say that we are using a linear behavior. It is not necessary that every material will behave like this, but most of the materials that we deal with, they will behave like this. For example, steel, for example, aluminium, to a certain extent wood. What do we do with this? Well, we'll find out the total work done. Okay, so total work done will be F into dx. This you are all familiar with. Okay, the limits of integration will be from what to what? Will be from 0 to delta. Okay, this F I am going to replace by this P divided by delta into x. There is this dx. So overall what this will become? P by delta into delta square by 2. So this is half P into delta. I am not trying to insult your intelligence, okay? I know all of you know this, but this is going to be the basis of all the advanced things that we are going to do. That is why I recapped it. Okay, on the basis of this, motivated by this, we'll do everything else. All right, so please understand that whatever we do from now, at the fundamental of it, remember that we are always presuming linear behavior. Okay, in fact, Castigliano's theorem that we do, uh, one of the assumptions behind it is that the behavior is linear. Okay, there are lots of other assumptions behind it, but this you must remember. Okay, so now that we have understood it, If you have found out the W, this is the work done, but this also happens to be the change in the strain energy. Okay, because W is equal to delta U. Okay, let's proceed. Now see, this is very good, half P into delta, but it is a little bit inconvenient in the sense that everything that we have been dealing since the first chapter has been in terms of stresses. Is it not? All those normal stresses, shear stresses and everything. So would it not have been a little bit more convenient for doing our problems if we can recast this relationship in terms of the stresses? So that is what we are going to do. We know about two different kinds of stresses, very broadly speaking, normal stresses and shear stresses. So we are going to first take up normal stress and then we are going to take up shear stress, and we'll see how the change in the strain energy is depicted in both the cases. So first, normal stress. Okay, so think of it like this, that you have this kind of a chunk of material. Here you have this sigma xx. This is dx, this is dy, and this over here is dz. As simple as that. Now P is the force, sigma xx is the stress. So on this little element that we are considering, what is the depiction of P? How can I write P? Sigma xx into the corresponding area. Okay, so sigma xx into the corresponding area will be what? Dy into dz. This is my P. What is my delta? Please be very careful. It should be in the direction of dx, but it itself is not dx because dx itself is the original length. Okay, but you know what I'm asking. I'm asking you to tell me the change in the length. Okay, what is the change in the length in the direction dx? Yes, it is epsilon xx dx. Okay, so you see how it is. It is something like this. Epsilon xx is equal to delta divided by dx, because here dx, even though it's an infinitesimal length, it is the original length. So over that there is a small delta. Okay, it is as if the original length was dx, it has now become dx plus delta. Okay. All right? Not all right. This is very, very important. Don't laugh. Why I'm saying this is, there was one guy, okay, who had done his PhD. Please edit this out. Dangerous things I'm saying. Okay, should not go public. So there was this guy who had done his PhD at IIT Kharagpur only. Very, very nice. Very nice. Okay, nice person, very good academically, excellent work, nice papers. But he had applied for a faculty position here at IIT Kharagpur only in our department. And in the faculty presentation, the interview kind of thing, not the interview happens in director's office, the departmental level presentation, somebody asked him this basic question, not me. Okay, not me. Somebody asked him this question and he fumbled. That created a very, very bad impression. he ended up not getting the faculty position. But good for him, he ended up at IIT Delhi. Now, don't go searching in IIT Delhi who are the young people who have gotten PhD from IIT Kharagpur. I don't want to dox him. Please edit it out, okay? रोहित का दिमाग खराब हो रहा है, उल्टा पल्टा बात बोलेगा आदमी. Okay, so this half is very important. Okay, this half, please note, is arising fundamentally because of this linear relationship. Okay, and we are proceeding from the zero deformation to that final deformation, both the things. Okay, from zero deformation to delta as well as this linear relationship. That is why that half is appearing. Had it not been the linear relationship, it would not have appeared. Okay, only because this thing is there, no, this x is there. That is why that x square by 2 is coming. Okay, now this entire thing can be rewritten in a very nice fashion. Half sigma xx epsilon xx. And we write dx, dy, dz. This entire thing is what? It is the elemental volume. Okay, this is the elemental volume. Now, what is this thing that we have done? This is the incremental change in the strain energy. Is it not? So, we are not going to write it as delta U, rather we are going to write it as du. Okay. So, this entire thing, so I'll write it here only. Okay. So, this is du. So, du is equal to half sigma xx epsilon x dv, which means that I can write this thing as du dv is equal to half sigma xx epsilon xx. Now tell me, if du is the change, that little incremental change in the strain energy, and I'm taking this with this dv, what is this thing basically representing? Forget the calculus for a moment, just think of it in terms of infinitesimals. Du divided by dv. Okay. I am not doing any mathematical crime by saying it is like du divided by dv. Had it been a partial derivative, then it is completely a mathematical crime to say like that. That del u del v is not del u divided by del v. But du dv can be interpreted as du divided by dv. Okay. So this thing is what? What is the unit? Unit is, this one is what? Joules. Okay, joules. And this is meter cube. So this is joules per meter cube. Okay, so this is what? Change in internal energy per volume. Okay, so this is what is referred to as the the strain energy density. Okay, so we'll call it this thing. Okay, so this is the strain energy density. Yes.
Only for the mathematical convenience we plugged in a half or it is
We have not plugged in a half. We have not plugged in a half. This, I am using this thing. I am using this thing. Okay, half P into delta. That is what I am using. Because I have already proved to myself that the work done on a body where a force is being applied and which is behaving linearly, that will be the expression. Okay. All right. Next, shear. Okay. What we'll do now is we are going to consider this shear. What is this? This is tau yx, but we'll call it tau xy only. Okay, tau xy is equal to tau yx. And again, just like before, this is dx, this is dy, and this is dz. Now, if this shear is present, how do you think this entire thing is going to deform? It is literally going to shear, the upper surface is going to slide a little bit. Okay, so the entire thing will get deformed like this. Okay, it will get deformed like that. Now you tell me, what do I write for that half p into delta? So again, this du thing, half. For the force, what is the appropriate force in terms of the tau xy? Tau xy dx into dz. This should be multiplied with the deformation. The deformation is what? This is the deformation, right? This part is the deformation. How much is it? It is gamma xy into dy. So overall it becomes half tau xy gamma xy. So again, our u naught in this case is du dv, that is equal to half tau xy gamma xy. These little things that I am telling you, you may think that okay, I mean, but later on also when you do more advanced things, you will see again these kinds of things coming up in long expressions, in very general expressions. Again, these things will come up. So it is, I think, appropriate that we are spending some time in understanding these things in a very simple fashion. Okay, so we have tried to wrap our head around this normal stress and the shear stress cases. Now all that you have to do is go into the different kinds of chapters that we have already done. What are the chapters that we have done? We have talked about torsion, we have talked about flexure, we have talked about shear. Okay, so all those things that you have done separately, they can be recast in terms of these things, because in each of those chapters, ultimately it all boiled down to a normal stress or a shear stress. Okay, so all those things we will, and plus the tutorial sheet number 0, barring the temperature part, okay, all those axial things, that also we will talk about. So axial with normal stress, torsion with shear stress, flexure with the normal stress, and shear with the shear stress. So that's what we'll do. Okay. The question which we ask ourselves is that if we have a mechanical member and we apply some kind of axial load on it, then what is the change in the strain energy of the body or the member? So delta U is going to be equal to integration of du. Okay, integration of du. This thing Okay, du dv is equal to u naught, and u naught is equal to either half of sigma xx epsilon xx or half of tau xy gamma xy, as we have just proved there. Okay, now when you have axial load, what is the stress? What is the relevant stress? It is the normal stress, so we'll write in terms of the normal stress. Now, till now I have not drawn any picture, but you just have this picture in your head that we are considering some kind of a member like this, that it is a beam or a shaft, okay, where you have some load here. So we are considering the axial load like this. Okay, this is the kind of picture that we have in our mind. It can be a circular cross section, elliptical cross section, whatever, but this kind of a member. Now, what is epsilon xx in terms of sigma xx? Well, in general, by the generalized Hooke's law, we have this relationship. Right? But in order to keep things very, very simple, like almost KG level mechanics, so we are going to neglect these contributions. Or equivalently, what you can say is that for now, we are neglecting the influence of this Poisson's ratio. Okay, so see, in general, what I just did in a very careless manner, this is not going to be true. Okay, if you do an actual problem, you will see that these kinds of things don't happen just like that. Okay, but here we're just trying to find some simple expressions, so we'll do it. Okay, all right. Where do we go from here? Sigma xx can be depicted in terms of the actual loading which is there on the body. How can I write the dv if I tell myself that I want to just consider the volumetric element corresponding to a slice of material? Then dv is equal to a dx. And the moment you write this dx and you remember that in front there is an integration sign, now we are it's very convenient for us to write down the limits of that integration. Okay, because this x will go from one end of the member to the other end. So here we can write this 0 to L, the entire length of the member. Because I am writing these kinds of things, please understand that this kind of a formulation, it is not applicable to any which member. Okay, so only for these kinds of members which you have studied within the context of your axial loading chapter, only for those kinds of things this formulation is applicable. Be that as it may, we proceed. This is it. That's it. Okay. So for axial loading, the relevant expression is this integration 0 to L p square by twice AE dx. Some of you have a bent of mind where you understand things, but then it kind of irritates you and annoys you when the teacher doesn't tell you where we are going with it. So for those students, let me just tell you beforehand, there is a reason why we are slowly building up these formulas. So ultimately, when we solve the problems using Castigliano's theorem, we have to start from somewhere. We have to write the various expressions of the energy corresponding to various loading cases. So there you will see that the various members will be subjected to bending, to axial loading, to torsion, to shear, and for that we have to write down these various expressions. Okay, sometimes in combination, maybe with torsion with flexure, just like you have done in the case of the combined loading chapter. Okay, so like ultimately we are preparing ourselves for Castigliano's theorem. Okay, or the application of Castigliano's theorem. So this is done. Next is bending. In bending, what kind of stresses are involved? Flexural stresses. What are the flexural stresses basically? Are they normal stress or shear stress? Normal stress, because sigma is equal to my by I. That is a normal stress. Okay. So again, our delta U will be this du. This will be du dv. This will be equal to u naught dv, and this will be half of sigma xx epsilon xx dv. Up to here, no change. Even the next step, this also no change. In fact, the next step also. But now we have to write down the expression for the sigma. So now this dv, earlier we had written it as a dx. When we write it a dx, say ultimate, try to think of it like this. The dv, originally it was made up of that dx, dy, dz. When we write a dx, what are we doing? We are already doing an integration over the cross section. But in reality, is it not something like this, that we have this dA into dx? Okay, this thing is there. Okay, now this dv can indeed be written as this dA into dx. Now because there are two differentials here, it is not enough for us to write this with one integration. Okay, whenever we are writing like this integration with respect to the dv, we understand that this integration is actually over the volume. It is actually a triple integral. Okay, we are just being lazy not to write the triple integral every time. But now that we have explicitly written this with two differentials, it is not quite right to write like this. So we have to write this with a double integral. So this integration from 0 to L is with respect to the dx. And this inner integral, this is with respect to the entire cross-sectional area. This is not a lower limit, okay? This is just the integration with respect to the entire area. Now you tell me, within the cross-section, is the M changing? Within the cross-section, is the M changing? Certainly not. M is changing with respect to X. You have done so many shear force bending moment diagrams, right? So m is changing with respect to x, not within the cross section. Young's modulus, no. Okay. I, again a property of the area, so it is not varying with the area. So all of these things can be taken out of this integration with respect to the dA. And what is this particular combination? This is nothing but the I itself. So what we have is this thing, which means that this is this. So earlier we had obtained this thing for the axial load. For the bending, we are obtaining this. These are extremely important. Time and again we have to utilize this. Next, we are going to consider torsion. Now, we have to be careful. This strain energy density U naught, earlier in both the cases, the axial loading and the bending, we depicted them in terms of we expressed them in terms of the normal stress. But now this torsion, what is it associated with? With the shear stress. So we have to accordingly do this. Now tell me, although while building up our basic formulation, this dV was written in terms of the dx, dy, dz. But now, if we are interested in finding out the change in the strain energy corresponding to this kind of a member, this is a shaft which has a circular cross section. Which kind of a coordinate system is more natural to it? It is the cylindrical coordinate system. So we will write this dV in the cylindrical coordinate system. Okay. So earlier in the longitudinal direction, the axis which you had was x, but now it will be z. Okay. This u naught I will write in terms of the shear, and there will be a gamma, tau into gamma. But tell me, what should be the appropriate subscripts here? Go back to the torsion chapter and tell me. So we are considering the shear stresses which are there on this cross section. Okay, on this flat cross section. It will be tau z theta. If you don't remember, go back to the torsion chapter and revise a little bit. So this is tau z theta. This dV I will write like dA into dz. Okay, dA into dz. Again, there are two differentials, so I'll have to write them properly with a double integration. The integration limits for the integration with respect to z, that will be going from 0 to L. But for this integration with respect to dA, I have to be a little bit careful in how I depict the dA. Okay. The gamma z theta, how can I write in terms of the tau? Earlier I wrote the epsilon xx as sigma xx by E. How can I write the gamma z theta? Tau z theta by the shear modulus. G is the shear modulus. This dA, I will borrow from your knowledge of +2. How did we do it? Do you remember this? For various kinds of gravitational problems and the electrostatic problems, twice pi r dr. Here also, please note explicitly that this twice pi is coming because we have already done an integration with respect to theta. Okay, so from 0 to twice pi we have gone. Because this entire thing is axis symmetric, we do not have to worry about the variation along the theta direction. Anyway, so this is, I believe you all know this. So why am I interested in writing this in terms of this r? Where am I going with this? Because you see, already I have written this in terms of this tau z theta square. This tau z theta will be what? In terms tr by j. Very good. Okay, so tau z theta will be written as tr by j. Okay, t is supplied to us. J is the property of the cross sections. The only thing that we need to worry about is that r. Okay, that is why we need this thing. By the way, acha, let me write it down. This is t square r square divided by twice g j square. So I've just substituted tau z theta is equal to tr by j. Now I am free to write the proper limits of this r. R is going from 0 to capital R. Now in this integration with respect to r, do you think the capital T is varying? No, certainly not. 2 is not varying, G is not varying, J is also not varying. Okay. Okay. So we just have to finish up this integration. So you see what this is? This is basically pi r to the power 4 by 2. Okay, which is nothing but the j itself. Okay, so so this is the formula for the torsion case. Now before we take this 5-minute break, I just want to tell you something here. See, here you got 0 to L m square by twice EI. In the denominator, what you have? You have the Young's modulus, which is a material property, combined with this I, which is a property of the cross section, a geometrical property of the cross section. In a similar fashion, in the denominator, here you have this material property G and this property of the geometrical property of the cross section J. In the numerator, you have the loading, the source of the loading. Okay, the loading source T. Here also it is the loading source M. If you look at the formula for the axial load, which I have erased from the board, it was look at your notes, integration 0 to L, it was P square by twice AE. In the numerator, it was again the loading source. In the denominator, one was the material property Young's modulus and the other one was the area of the cross section, which is a geometrical property. So time and again we are encountering this form. Okay, so the only thing left now is the shear force case, but let's take a break first.